Deep in the constellation Phoenix lies a black hole so powerful it outshines entire galaxies. Astronomers call it Phoenix A, a cosmic engine, unlike anything we've seen before. Tonight we'll uncover why it has earned that title. If this fascinates you, please like, subscribe and share, and tell us in the comments, what do you think could exist beyond a black hole this powerful? Thank you for watching. Now let's begin. Across the deep sky, far beyond the bright sweep of the Milky Way, lies a congregation of galaxies bound together by gravity and time. Astronomers call it the Phoenix Cluster, a system so distant that its light has travelled billions of years to reach Earth. In telescopes, it appears not as a single body, but as a web of pale arcs and faint knots of starlight suspended in darkness. What unites them is the hidden weight of dark matter and a shared bath of hot diffuse gas that glows in X-rays. The Phoenix Cluster occupies a region hundreds of thousands of light-years across, large enough to contain hundreds of galaxies, each one carrying its own black hole, its own stellar history, and its own dust-laden outskirts. Yet despite its population, the cluster acts almost as one living structure held together by the immense gravity of its collective mass. In space, gravity is the sculptor of time, and here it has gathered ancient material into a single gravitational basin, an enormous well, where light struggles to escape and heat lingers in thin air. The gas between these galaxies is not the cool kind that flows quietly through spiral arms. It is plasma matter, stripped of electrons, heated to tens of millions of degrees Celsius, thin as a whisper, yet vast beyond comprehension. From this glowing envelope, X-rays pour into the void. When the Chandra X-ray Observatory looked at the Phoenix Cluster, the instruments saw not a uniform haze, but subtle gradients of brightness, signs that energy moves through this environment unevenly. The space between galaxies is often imagined as empty, but in a cluster like this it is filled with a tenuous fog that carries more mass than all the stars combined. This intracluster medium behaves like a delicate fabric responding to the disturbances of every passing galaxy, every shock wave and every gravitational tremor from the center. Embedded in this structure, gravitational fields weave and pull, bending the path of light and distorting the background universe into faint arcs of magnified glow, gravitational lensing the cosmic signature of unseen mass. Within this luminous fog, each galaxy drifts in slow motion, orbiting the cluster's core as if trapped in an invisible whirlpool. The scale is so great that no single human lifetime could see a measurable change in their positions. Yet in astronomical time, these movements shape the structure of the cluster, gradually feeding its heart with matter. Every motion, every collision, every faint trace of dust falling inward contributes to a slow but relentless accumulation near the center. The Phoenix Cluster is not static. It evolves, consuming and reshaping itself over cosmic ages. The vast halo of hot gas functions as both a record and a regulator of that evolution. As it radiates X-rays, it loses energy and tends to cool, creating conditions that can lead to the condensation of denser material. Normally, such cooling would spawn cascades of cold gas and bursts of new stars, but in most clusters, something prevents this process from running unchecked. Observations show that central black holes buried deep within the brightest galaxies inject energy back into their surroundings, reheating the gas and slowing star formation. This delicate balance between cooling and heating keeps most clusters in a quiet equilibrium. The Phoenix Cluster, however, hints that this balance may not always hold. Its central regions shine far brighter than expected, suggesting that cooling and star formation continue even as powerful energy emerges from the core. Seen in visible light, the cluster's central galaxy is enormous, a giant elliptical that dominates its surroundings. Its halo extends so far that it blends into the faint background of neighbouring galaxies. This dominant structure is called the brightest cluster galaxy, the gravitational anchor of the entire system. Around it, smaller galaxies orbit like satellites, and between them streams of intra-cluster light flow from the remnants of past mergers. The centre of gravity rests here near a point invisible to any optical telescope, the location of the supermassive black hole known as Phoenix A. At this stage, however, the narrative remains in the outer regions. From a distant vantage point, Phoenix A cannot yet be distinguished. What is seen instead is the combined brilliance of a cluster in motion, radiating energy from millions of stars and from plasma heated to extreme temperatures. The cluster's total mass is estimated to be in the range of quadrillions of times that of the Sun, a number so large it defies easy intuition. This mass bends space-time itself, forming a basin where energy and matter orbit in slow choreography. The atmosphere of the cluster is a turbulent domain. The hot gas that fills it emits light in the X-ray part of the spectrum, but within that glow, astronomers have detected structures, depressions, and waves that hint at dynamic processes. These patterns are not the product of simple gravitational settling. They are the marks of immense forces pushing outward from within. The Phoenix cluster in that sense is both an environment and an event, a place where extremes of temperature and gravity interact in continuous dialogue. On its outskirts, galaxies are still falling inward from the cosmic web drawn by gravity across tens of millions of light years. Their approach stirs the plasma, generating shocks that ripple through the medium. These infalling systems carry fresh material gas, dark matter, and stars into the gravitational heart. In time, friction and tidal forces will strip them of their outer envelopes, leaving trails of stars that merge with the cluster's diffuse halo. Through this process, the cluster grows. The name Phoenix evokes rebirth, and the cluster lives up to it. Observations show that while many galaxy clusters have settled into quiet stability, this one is unusually active. Its center glows not only in X-rays but also in infrared and ultraviolet light, each band telling of complex physical conditions. The infrared suggests dust and star formation. The ultraviolet reveals streams of hot young stars. Together they describe a system where cooling and heating proceed side by side, a sign of intense and recent change. To grasp the immensity of this place is to imagine an environment where distances are measured not in millions, but in hundreds of millions of light years, where single galaxies become small participants in a structure larger than imagination. The Phoenix cluster's location in the southern sky places it near the border of the constellations Sculptor and Tucana, visible only to the largest telescopes. From Earth, it is one of the most luminous X-ray clusters ever found, its radiance a clue to the hidden engine buried deep within its core. This first view sets the stage, an environment vast and ancient, still in motion, filled with heat, light and gravity. The outer regions reveal the scale of the system, the gentle drift of galaxies, the glow of plasma, and the quiet balance between cooling and heating that defines cluster life. But even here, faint ripples suggest that something powerful stirs within an unseen source, shaping the cluster's temperature, sculpting its cavities, and sending waves of energy through its gaseous sea. In the calm glow of the X-ray sky, the Phoenix cluster reveals both beauty and imbalance. Its outer edges shimmer with the light of collective history, while its inner heart begins to hint at a power that astronomers would come to call the most extreme yet measured in the universe. From the quiet outskirts of the Phoenix cluster, the view deepens toward its luminous center. What begins as a faint haze of light in visible wavelengths transforms under X-ray observation into a brilliant and complex panorama. In this spectrum, invisible to human eyes, the cluster becomes an ocean of heat and energy, its gases shimmering at tens of millions of degrees Celsius. The Chandra X-ray Observatory captures this radiation as a structured glow mapping the density, temperature and pressure of plasma that fills the spaces between galaxies. Every photon of X-ray light is born from violent collisions between electrons and ions in this thin, superheated medium. Where the light is brightest, the gas is densest and hottest, pressed by gravity toward the cluster's core. This environment is known as the intracluster medium, a plasma sea that accounts for most of the ordinary matter in galaxy clusters. Unlike the gas that forms stars, it is so hot that atoms cannot remain whole. Instead, protons and electrons move independently, creating a diffuse cloud of charged particles that constantly emits energy through a process called bremsstrahlung, or breaking radiation, as electrons are deflected by atomic nuclei. This radiation fills the cluster like a faint heartbeat, slow and steady, detectable only through high-energy telescopes orbiting above Earth's atmosphere. The Phoenix cluster's X-ray luminosity surpasses almost all others known. It radiates with the energy of trillions of suns, a scale that reflects both its enormous mass and the physical violence within. Its glow is not uniform. Subtle gradients trace shock fronts, ripples and elongated cavities carved by forces emanating from the central region. In the quiet background, these forms are easy to overlook, yet they carry the imprint of immense power. The cavities are not empty space, but regions where hot gas has been displaced by jets of relativistic particles streaming outward from the core. They mark the memory of past eruptions when the central black hole injected energy into its surroundings. The contrast between luminous gas and these darker pockets forms the first visual clue to what lies hidden at the heart of the cluster. Each structure is vast, stretching for tens of thousands of light years. If placed within the Milky Way, one cavity could engulf the entire galactic disk, yet the forces that carved them remain invisible in direct light. They reveal themselves only through the pattern of missing X-rays, a negative image of activity so powerful that it alters the thermodynamic balance of the cluster. These features tell astronomers that the Phoenix cluster is not passive. It is dynamic, shaped by cycles of release and recovery. The gas cools as it radiates energy away, drifting inward until it triggers renewed outflow from the central engine. This interplay of cooling and heating defines the rhythm of cluster life, and in Phoenix the rhythm is fast, loud and unrelenting. The spatial structure of the X-ray glow provides a map of pressure and motion. Near the center, brightness peaks sharply, indicating a dense, cool core, a rarity in clusters where feedback usually prevents excessive cooling. Such a bright central region implies that gas is losing energy quickly, condensing toward the middle and feeding both star formation and black hole growth. Around this core, a fainter halo extends outward like a diffuse cocoon, its temperature climbing with radius as energy disperses. This temperature gradient offers clues about how the cluster evolved. In most systems, outer gas remains hotter because it has been shock heated by infalling material. Here the difference between core and periphery is more pronounced, suggesting that the balance of heating and cooling has tilted, perhaps only temporarily, toward collapse and regeneration. Observations from multiple instruments: Chandra for X-rays, Hubble for optical light, and the South Pole Telescope for microwave data, combine to portray a layered structure. The microwave signal reveals a dip where the cluster's gravity bends and compresses the background cosmic radiation, an effect known as the Sunyaev-Zeldovich signature. This allows scientists to estimate the total mass which includes both visible and dark components. X-ray measurements, in turn, show how that mass is distributed within the gas. Together, they outline an extraordinary equilibrium, gravity pulling inward, thermal pressure pushing outward, and at the center, a hidden force periodically disrupting both. Within this environment, temperature alone defines an alien landscape. At tens of millions of degrees, matter behaves as a fluid of charged particles. Magnetic fields, though weak by human standards, can shape its motion over colossal scales, guiding flows along invisible lines and creating filaments that stretch across hundreds of thousands of light years. These filaments appear faint in X-rays but shine in other wavelengths, particularly in optical and radio observations. They act as conduits for energy, transporting heat and momentum away from the core. The Phoenix cluster exhibits an unusually complex network of such structures, indicating both active outflows and regions of rapid cooling. In the stillness of the cosmic background, these interactions unfold slowly, yet they represent one of the most energetic processes known. The total thermal energy stored in the intracluster medium exceeds what all the stars within could release in their combined lifetimes. This energy reservoir keeps the cluster luminous. Even though its constituent galaxies evolve independently, their starlight faint compared to the collective radiance of the gas around them. The cluster thus becomes a paradox, an object of light, built not from stars but from matter, too hot to form them. When astronomers study this light, they read the cluster's history written in temperature and density. Sharp edges in the X-ray image mark past shocks, remnants of collisions between subclusters, or the aftereffects of massive eruptions. Gentle ripples arranged like rings record acoustic waves moving through the plasma, stirred by bursts of energy from the nucleus. These waves dissipate slowly, distributing heat through the surrounding medium and delaying the onset of large-scale cooling. Each pattern, each curve of brightness corresponds to a distinct physical event. Through them, researchers reconstruct a timeline measured not in years but in millions of years, tracing the cluster's heartbeat as it expands, cools, and reignites. The Phoenix cluster stands out not only for its brilliance, but also for the subtle asymmetry of its light. One side of its core glows more intensely than the other, suggesting directional motion of gas or uneven feedback from the central source. This imbalance hints at jet activity, narrow high-velocity streams of plasma launched from near the event horizon of a supermassive black hole. Though these jets are not directly visible in X-rays, their influence spreads through the entire system. They push back the surrounding gas, inflating the cavities and stirring turbulence that can persist for millions of years. Even at this outer stage of exploration, the signs of their presence are unmistakable. As the gaze moves inward, the brightness intensifies, the patterns of the X-ray light converge, and the evidence points toward the cluster's core. There, behind layers of glowing plasma and drifting galaxies, lies the source of the disturbance, the giant elliptical galaxy known as Phoenix A. At its center, beyond the limits of direct vision, a black hole hundreds of millions of times more massive than the Sun feeds on infalling gas, releasing energy that shapes the cluster's form and fate. Yet for now, the perspective remains within the landscape of light itself, an environment vast, hot and restless, illuminated by processes that operate silently across cosmic time. The Phoenix cluster's glow is not a mere background phenomenon. It is the physical expression of gravity and energy in constant negotiation, a conversation that extends from its calm periphery to the unseen depths where the true engine waits. At the cluster's luminous heart, the X-ray glow shifts from smooth gradients into disturbed patterns, as if invisible hands have stirred the plasma. The once even halo now bears hollows and arcs, edges where pressure has changed abruptly, and ripples that radiate outward like the memory of a distant explosion. These features are faint but unmistakable. They speak of energy released deep within the center energy, strong enough to move matter across hundreds of thousands of light years. In the quiet image of the Phoenix cluster, these distortions mark the restless core where gravitational and magnetic forces work together to shape a complex and dynamic environment. The evidence of activity first appears as pairs of cavities, enormous voids, where the normal X-ray brightness falls away. Each cavity measures tens of thousands of light years across, suggesting that something has pushed aside massive quantities of gas. Astronomers interpret these voids as the imprint of radio jets, narrow streams of charged particles ejected at nearly the speed of light from near the supermassive black hole at the cluster's center. As these jets penetrate the surrounding plasma, they inflate lobes of relativistic particles that displace the hot gas, forming low-density bubbles. These bubbles rise buoyantly through the cluster's atmosphere, much like air bubbles rising through water, dragging trails of cooler material behind them. Over time, their ascent spreads energy throughout the core heating gas that might otherwise condense and form stars. The pattern of these cavities tells a story of cycles. They are not random in position or size, but appear in aligned pairs indicating repeated eruptions along roughly the same axis. Each outburst must have lasted for millions of years, releasing more energy than a million supernovae combined. Yet between eruptions, the central engine grows quiet, allowing gas to cool once more and drift inward, preparing for the next cycle of activity. This alternation between violence and calm defines what astronomers call feedback, a process that regulates both the black hole's growth and the cluster's evolution. In Phoenix, however, the scale of feedback appears extreme. The cavities are larger and deeper than in most clusters, and the energy required to create them is among the highest ever measured. Such power suggests that the black hole's outbursts are not merely local events, but phenomena capable of shaping the behavior of the entire cluster core. Beyond the cavities, faint arcs trace the path of shock waves. These are regions where gas has been compressed and heated as expanding lobes of plasma pushed against the surrounding medium. The shocks move outward slowly by cosmic standards, perhaps a few thousand kilometers per second, but their influence endures for millions of years. They smooth temperature gradients, redistribute pressure, and spread energy evenly through the intracluster medium. Each ring-like feature is a snapshot of an earlier eruption frozen in light. By measuring their size and brightness, astronomers can reconstruct the timing and strength of past events, turning the X-ray map into a record of the black hole's long-term activity. In the Phoenix cluster, that record is unusually rich. The multiple generations of cavities and shocks indicate a continuous series of outbursts, each adding new layers to the evolving structure of the core. Radio observations confirm this history. At wavelengths invisible to the eye, the central region shines with the glow of synchrotron radiation, produced by electrons spiraling through magnetic fields at near light speeds. The radio lobes coincide with the X-ray cavities, confirming that both mark the footprints of the same process. In some places, faint filaments of radio emission extend even farther, hinting at past episodes of greater reach. The geometry of these structures shows that the black hole's jets have shifted directions slightly over time, perhaps due to changes in the spin of the black hole or the motion of gas feeding it. This slow drift adds complexity to the core, ensuring that no single eruption follows precisely the path of its predecessor. In optical and infrared wavelengths, the cluster's heart reveals yet more complexity. Streams of cool gas thread through the bright central galaxy, forming filaments that curve and twist in patterns shaped by magnetic fields and turbulence. These filaments trace the flow of matter from outer regions inward, carrying fuel toward the black hole, even as other forces drive gas outward. The coexistence of inflow and outflow gives the core its restless character, a place where gravity, radiation, and magnetism compete without clear dominance. The inflowing material is drawn from the cooling intracluster medium, condensing as it loses energy. As it approaches the nucleus, some of it forms stars while the rest crosses the event horizon and disappears. Each act of feeding ignites new eruptions, ensuring that the cycle continues. The scale of disturbance becomes clear when the total energy involved is estimated. The power required to create the observed cavities exceeds 10 to the 45th watts, a number so vast that it dwarfs all the starlight from the cluster's hundreds of galaxies combined. This outflow not only sculpts the X-ray plasma, but also influences how stars form and how gas circulates on scales of hundreds of thousands of light years. It is as though the black hole, an object smaller than the solar system, exerts control over a region billions of times its size. This remarkable coupling between small and large, between singularity and cluster, defines the mystery of Phoenix A. Despite its apparent turmoil, the core maintains an eerie stability. The outflows, though powerful, do not expel all the gas. Instead, they create an equilibrium in which heating and cooling nearly balance. Gas cools, condenses, feeds. The black hole triggers an outburst and is reheated, a cycle that prevents either runaway collapse or permanent quiescence. In Phoenix, this equilibrium may be temporarily tipped toward cooling, explaining why the central galaxy forms stars at a prodigious rate. Even so, the presence of cavities and shocks shows that the feedback mechanism remains active, striving to restore balance. The restless core also leaves imprints beyond temperature and brightness. Spectroscopic studies reveal motions of gas approaching and receding at thousands of kilometers per second. These Doppler shifts expose turbulent eddies stirred by the black hole's jets. In this turbulence, energy is slowly converted into heat, spreading through the plasma and damping extreme cooling. Such turbulence is invisible in static images, but becomes clear through subtle shifts in spectral lines, allowing scientists to infer movement within what appears otherwise serene. As telescopes probe deeper, the impression of movement grows stronger. Patterns repeat on smaller scales, miniature cavities, nested ripples and filaments, all aligned toward the center. The geometry suggests that the black hole's activity is not confined to brief bursts, but continues through overlapping phases. Energy, once released, travels outward as both mechanical motion and radiation, affecting gas far from the nucleus. Some of the rising bubbles may even reach the cluster's outskirts before dissipating, ensuring that the entire system feels the consequences of central activity. To an observer studying this structure, the Phoenix cluster's core seems less like a tranquil center and more like a living system sustained by alternating breaths of energy. Each eruption feeds the next. Each disturbance smooths into the background only to return in a new form. The gas cools, collapses and ignites again, while the black hole at the center, unseen but commanding, drives the rhythm. In the still light of observation, the signs of this restlessness are quiet yet unmistakable. The curved walls of cavities, the faint arcs of shocks, the subtle imbalance in temperature. Together they tell of a core that never truly sleeps, where cosmic forces continue their slow dialogue, shaping one of the most powerful systems ever recorded by human instruments. At the center of the Phoenix cluster sits a single galaxy, more massive and more radiant than any of its neighbors. This object is known as the brightest cluster galaxy, a type of giant elliptical galaxy that commonly forms at the bottom of a cluster's gravitational well. In the Phoenix cluster, that galaxy is called Phoenix A. It is the dominant structure in the core, surrounded by tidal debris interwoven with cold filaments and embedded in a cloud of very hot gas. Phoenix A gathers material from all directions, not only from its own extended halo, but from the slow inward drift of the cluster's atmosphere. Over cosmic time, smaller galaxies have fallen into it and been absorbed. Their stars now orbit in diffuse streams, erasing any sharp edges or spiral patterns, and leaving behind an enormous, smooth, rounded profile. Seen in optical light, Phoenix A does not display the familiar winding arms of a spiral galaxy. Instead, it appears as a diffuse swollen glow with a bright concentrated core. The light profile fades gradually with distance, not ending cleanly, but blending outward into the intra-cluster light that links the core to the surrounding environment. This kind of envelope signals both the depth of its gravitational influence and the number of past mergers that built it. Phoenix A is not young. It is the end product of repeated collisions, a galaxy grown fat on the remains of others. To understand why this single galaxy matters, astronomers turn not only to optical telescopes, but also to instruments that study X-ray radio and infrared light. The first surprise was that the region around Phoenix A is unusually bright in X-rays, brighter than expected for a core that should be stabilized by feedback. The second surprise was that the same region is also bright in ultraviolet and infrared light, which trace recent star formation and dust. This combination is rare. In most galaxy clusters, energy from the central black hole suppresses star formation in the brightest cluster galaxy, keeping it red and quiet. Phoenix A breaks that pattern. Its core carries the signs of both intense heating and intense cooling at the same time. That alone demands an explanation. The next step was to examine the very center of Phoenix A, where the gravitational pull becomes extreme, and the light profile steepens into a bright point-like region. This innermost zone is where the activity concentrates. Observations in radio wavelengths revealed jets emerging from the nucleus, extending outward and aligning with the large X-ray cavities in the surrounding plasma. Such jets are the classic signature of an actively accreting supermassive black hole. Where ordinary starlight fades into smooth background glow, the radio emission declares unmistakably the presence of a central engine. The alignment of radio lobes with displaced X-ray gas locks the interpretation in place. The power that reshapes the cluster core originates here inside Phoenix A, where the black hole resides. Once this was recognized, astronomers began to measure the energy output not by what the black hole itself emits directly, but by what it does to its environment. Phoenix A's nucleus drives jets that punch through the surrounding gas inflate cavities, launch weak shocks and stir turbulence. These actions move and heat material on scales reaching tens and even hundreds of thousands of light years. The ability to displace so much plasma and leave such deep cavities is the marker used to classify this source as one of the most powerful known. The jets are not just features of the galaxy, they're engines that work on the entire cluster. In this sense, Phoenix A is the bridge between an object on the scale of the solar system and consequences felt on the scale of a galaxy cluster. The black hole in Phoenix A cannot be seen directly. No telescope resolves its event horizon. Instead, its presence is inferred from its effects and from the mass of the stellar core surrounding it. The stars in the inner region move at tremendous speeds, indicating that they are bound to a central mass far greater than any collection of normal stars could provide. By modelling these motions, researchers estimate that the black hole at the heart of Phoenix A is billions of times the mass of the Sun. A black hole of this size exerts such gravity that even light cannot escape once it crosses the event horizon. Yet before matter falls in, it heats, compresses and accelerates in a rotating disk. This disk, called an accretion disk, feeds the black hole and converts gravitational energy into radiation and mechanical outflow. The jets are launched from regions very close to this disk, likely along the rotational axis of the black hole itself. They carry away angular momentum and energy, forming narrow channels of plasma that escape at near light speed and continue outward until they strike the surrounding medium. Phoenix A is remarkable because the energy released by this process is unusually high. The cavities it leaves in the surrounding gas are extremely large and deep, and the pressure required to maintain them indicates extraordinary jet power. When scientists calculate how much mechanical work must have been done to clear those cavities, they derive numbers that exceed those of almost every other known system. This is why Phoenix A is often described as hosting one of the most powerful black holes in the observable universe. The power is not a claim about brightness in visible light. Instead, it is a statement about how forcefully the black hole can reshape its environment. The scale of impact makes Phoenix A more than a passive central galaxy. It is an active regulator of the cluster's core. Another striking feature of Phoenix A is the presence of cold gas near the core, arranged in long threads and knots. Ordinarily, in many clusters, the hot intra-cluster medium remains too energized to cool efficiently, because feedback from the central black hole continually reheats it. In Phoenix, A cooling proceeds more efficiently than usual. Gas that cools can condense into molecular clouds, and those clouds can collapse to form new stars. Observations of Phoenix A suggest that star formation is happening in the core at a rate far higher than what is typically seen in other brightest cluster galaxies. This is important because it implies that the black hole, though powerful, has not fully suppressed cooling. The system appears caught in a state where both rapid cooling and energetic feedback are proceeding together. That state may be temporary on cosmic timescales, but at this moment it offers a direct look at how gas flows, collapses, feeds and ignites in the deepest part of a cluster. The discovery of Phoenix A as a central engine of extreme activity did more than identify a single unusual galaxy. It provided a natural laboratory for understanding how gravity, radiation and cooling interact in some of the most massive structures in the universe. The Phoenix cluster is not merely a group of galaxies that happen to share a common envelope. It is a feedback ecosystem. Phoenix A sits at the exact center of that ecosystem in both a geometric and energetic sense. The galaxy marks the location where the gravitational potential is deepest, where the gas is densest, where cooling is fastest, and where the black hole has access to a steady supply of fuel. From that vantage point, the nucleus exerts influence far beyond its physical size. Seen this way, the emergence of Phoenix A in observational data is not just a point of identification, but a narrowing of focus. The outer parts of the cluster reveal the scale of the environment. The X-ray glow reveals its temperature and structure. The cavities and ripples reveal activity. Phoenix A is where these threads meet. It is the location in which diffuse hot plasma becomes cool filaments, in which those filaments become inflow, in which that inflow becomes accretion, and in which accretion becomes mechanical output powerful enough to carve the cluster's atmosphere. The deeper the view goes, the clearer the connection becomes between the state of the cluster and the behavior of its central galaxy. From here on, attention moves inward again toward the source of that power and toward the numbers that describe it. Once Phoenix A was identified as the cluster's engine, astronomers turned to quantifying what power means in a system so large and remote. Direct measurement of energy from a supermassive black hole is impossible. Light cannot escape from within the event horizon, and even the accretion disk, though bright, hides much of its energy behind dust and plasma. Instead, the method relies on observing the work the black hole performs on its surroundings. In the Phoenix cluster, this means analysing the cavity's shock waves and radio lobes sculpted into the surrounding gas. These features are not transient flashes but slow, physical deformations that endure for tens of millions of years. Each cavity is a record of an eruption, its size a measure of how much energy was released, and its distance from the centre a rough measure of time since it formed. By combining these details, scientists calculate the mechanical power output of the jets that inflated them, a value known as cavity power. The process begins with simple geometry. An astronomer traces the outline of a cavity in an X-ray image, estimating its radius and depth. Assuming it is roughly spherical or ellipsoidal, its volume can be calculated. The next step is to estimate the pressure of the surrounding gas derived from temperature and density maps of the intracluster medium. Multiplying pressure by volume gives the work required to displace the gas a first-order estimate of the energy involved. Dividing this energy by the age of the cavity, how long it would take to rise buoyantly to its current position, yields an average power output. When this procedure is applied to Phoenix A, the numbers become extraordinary. The cavities are immense, the surrounding pressure high, and the timescales long, producing energy outputs far greater than in any other cluster of comparable size. The result places Phoenix A among the most powerful known sources of mechanical feedback in the observable universe. The magnitude is easier to understand through comparison. In a typical massive cluster, cavity powers range around 10 to the 44 watts. Phoenix A exceeds 10 to the 46. That means that every second it releases as much mechanical energy as several thousand galaxies radiate in light. This energy does not appear as a bright flare but as motion, pressure and heat distributed through the cluster's gas. It stirs, turbulence drives waves and prevents the surrounding plasma from cooling too quickly. Without this energy input, the gas would collapse toward the center, forming stars at rates that would quickly consume available material. The black hole, by releasing its power, prevents such runaway cooling. Yet in Phoenix A, that prevention seems incomplete. Cooling still proceeds at a remarkable pace, producing stars faster than almost anywhere else in the nearby universe. The data imply that the feedback cycle is not perfectly tuned, and that the black hole's immense power alternates with brief intervals of relative calm, allowing cooling to surge ahead before the next eruption restores balance. The mechanical power inferred from cavities is only part of the total energy budget. Jets also emit radio waves produced by relativistic electrons spiraling along magnetic fields. The brightness of this synchrotron radiation depends on the energy of those particles and the strength of the magnetic field. By measuring the radio emission across different frequencies, astronomers estimate the age and energy distribution of the plasma inside the cavities. In Phoenix A, these observations confirm that the jets are recent and still active. The radio lobes remain bright, indicating a continuous flow of energy from the nucleus. This supports the idea that Phoenix A's black hole has not merely erupted once, but has maintained a near-constant output for millions of years, driving a sustained and powerful feedback process. The cavities, though striking, are not the only evidence of energy. The surrounding gas carries signatures of weak shock sound waves on cosmic scales. These waves ripple outward, heating the medium as they dissipate. In the Phoenix cluster, such ripples have been detected extending tens of thousands of light-years from the core, marking successive events of energy release. Each wave carries enough energy to reheat vast volumes of plasma, offsetting, cooling and stabilizing the cluster's atmosphere. When the total power carried by cavities, shocks and radio emission is combined, the resulting figure surpasses that of any other known system of its kind. It is this combination, not a single feature, that earns Phoenix A its title as the most powerful black hole measured through mechanical feedback. These estimates are conservative. The energy needed to inflate the cavities could be larger if their shapes deviate from simple geometry, or if hidden substructures exist along the line of sight. Moreover, the age of each cavity is uncertain. If the outbursts are younger than assumed, the true power must be even greater. Uncertainties aside, the evidence remains overwhelming. Phoenix A dominates the cluster's energy budget. Even the total luminosity of all its stars combined is trivial compared to the mechanical energy flowing from the central black hole. Astronomers also examine the efficiency of this process, how much of the matter falling toward the black hole is converted into energy. If the black hole's mass and accretion rate are known, and if the cavity power is measured, one can estimate how effectively gravity's pull becomes heat and motion. In Phoenix A, that efficiency approaches theoretical limits, suggesting that the accretion disk operates near its maximum capacity. The jets must be drawing power not only from accretion, but also from the spin of the black hole itself, through magnetic processes described by general relativity. This combination, rapid rotation and heavy inflow, creates a near-perfect engine converting gravitational energy into mechanical work across cosmic scales. Such precision in measurement has broader implications. Understanding how to translate cavity dimensions into energy output allows astronomers to compare clusters across billions of light-years and across cosmic time. It reveals that black holes regulate the thermal evolution of galaxy clusters throughout the universe. Without them, the intracluster medium would cool, condense, and produce a flood of new stars. With them, the gas remains suspended in equilibrium, its temperature sustained by periodic injections of energy. Phoenix A, with its enormous cavity power, represents one extreme of this cosmic balance. It shows that the link between a black hole and its environment can operate at magnitudes far beyond what was once imagined. Viewed in composite images, the Phoenix cluster's center resembles a multi-layered storm. X-rays reveal cavities as shocks. Radio waves trace lobes of plasma. Optical light shows filaments of cooling gas glowing faintly with newborn stars. Each wavelength tells a fragment of the same story, a hidden object releasing energy at scales no star could match, its effects rippling outward to reshape matter across hundreds of thousands of light years. The measurement of its power is not merely an academic exercise, but the key to understanding how such giants control the rhythm of cosmic structure formation. Through these indirect signatures, the voids, the ripples, the light of new stars, the invisible becomes known. Phoenix A's true size cannot be seen, but its strength is written across the cluster like a map, revealing in the quiet light of observation the scale of power that the universe allows a single black hole to wield. Deep within the bright elliptical glow of Phoenix A lies a process that connects the vast environment of the cluster with the smallest scales of gravity. All the light and heat that radiate from the intracluster medium, all the turbulence and structure that fill its core eventually lead to one outcome: the slow but steady feeding of the supermassive black hole. Feeding in this sense does not mean swallowing stars whole or consuming matter in bursts of visible violence. It is a quiet and continuous process carried out by gas that cools, condenses, and drifts inward until gravity takes over completely. The Phoenix cluster provides one of the clearest windows into this cycle of cosmic nourishment, a chain of events that begins far from the black hole and ends in a zone where the known laws of physics begin to fail. The hot plasma that fills the cluster constantly radiates energy in the form of X-rays. As it loses heat, its pressure drops and it starts to fall inward along the cluster's gravitational gradient. Normally, the feedback from the central black hole supplies enough heat to offset this cooling. But in Phoenix A, cooling has outpaced heating. The result is a torrent of material that condenses into cooler, denser filaments of gas and dust structures that can be traced in optical and sub-millimeter wavelengths. These filaments stretch for tens of thousands of light years, winding like narrow rivers through the hot atmosphere. They are cold by cosmic standards, with temperatures of only a few tens of degrees above absolute zero, and they carry enormous amounts of molecular hydrogen, the raw fuel of star formation and accretion. Observations from the Atacama Large Millimeter Array reveal that these filaments are not static. They flow slowly inward toward the galaxy's nucleus, guided by magnetic fields and pulled by gravity. Along the way, fragments of gas clump together to form new stars, while the rest continues to spiral toward the center, where the black hole awaits. The rate of this inflow is astonishing. Estimates suggest that hundreds of solar masses of gas cool and condense every year, a flow rate far exceeding what is seen in most clusters. Only a fraction of that material reaches the black hole directly. The rest builds stars or joins the cold reservoir that surrounds the nucleus. Yet even this fraction is enough to sustain extraordinary activity. A small percentage of the infalling gas is converted into energy, and because the efficiency of accretion is high, the resulting output in the form of jets and radiation dominates the entire cluster's energy budget. The black hole consumes matter slowly by human standards, but over cosmic timescales its appetite is enormous. Each gram of falling material is transformed into heat, light, and kinetic motion that travel outward through the cluster, linking the inner and outer regions in a continuous feedback loop. As gas approaches the central region, it enters a chaotic domain. Temperatures rise, magnetic fields intensify, and the rotation of the galaxy twists the flow into a spiral. The material flattens into an accretion disk orbiting the black hole at nearly the speed of light. Friction within the disk converts gravitational potential energy into heat, causing the disk to glow across the electromagnetic spectrum. Near its inner edge, temperatures reach millions of degrees, releasing ultraviolet and X-ray radiation that escapes along the poles. Part of this radiation is absorbed and re-emitted by dust farther out, creating the infrared glow observed by space telescopes. Beyond the disk itself, magnetic fields thread the plasma and channel part of it, away from the plane of rotation, launching twin jets that pierce the surrounding gas. These jets are the engines that carve cavities and drive shocks, but their origin lies in the orderly yet violent dynamics of this rotating disk only light hours across. The inflow of gas and the outflow of energy are not separate events, but two aspects of the same mechanism. Without a steady supply of matter, the black hole would become dormant. Without outflows, the surrounding gas would cool unchecked, flooding the core with material and altering the cluster's balance. In Phoenix A, the two processes are deeply intertwined. The accretion flow fuels the jets, and the jets in turn heat and disturb the gas that might otherwise feed the black hole too rapidly. This creates a natural form of regulation, though in this system, the equilibrium appears unstable. The cooling flow remains strong, and the feedback, though immense, does not entirely suppress it. The cluster thus finds itself in a state of heightened activity, where both feeding and feedback proceed together, driving the luminous and energetic behavior observed today. The presence of cold gas in close proximity to such a powerful black hole raises interesting questions about stability. Normally, radiation from the nucleus would heat or expel nearby material. In Phoenix A, the geometry of the flow may help preserve the inflowing filaments. The jets appear to vent most of their energy along narrow paths, leaving other regions relatively undisturbed. These quieter channels allow cold material to survive and reach the inner core. Once there, tidal forces stretch and compress the gas until it fragments, forming dense clouds that either collapse into stars or are shredded into the accretion disk. The process is slow, extending over millions of years, but it never truly stops. Each generation of inflow fuels another phase of feedback, which shapes the conditions for the next cycle. The feeding process also leaves spectral fingerprints, emission lines from ionized oxygen, nitrogen, and hydrogen reveal gas moving inward at thousands of kilometers per second. Absorption lines from cooler molecules show where dense filaments obscure the bright central region. Together, these signatures trace the motion of matter across scales that span 10 orders of magnitude, from hundreds of thousands of light years in the cluster's halo to a few light hours near the black hole's event horizon. They demonstrate that the power of Phoenix A is not born from a single eruption, but from an ongoing transaction between gravity and matter, one that repeats endlessly and maintains the cluster's internal structure. Astronomers studying Phoenix A often describe it as an example of cooling flow feedback in overdrive. The rate at which gas cools and the rate at which the black hole releases energy are both extreme. Yet this imbalance may not be permanent. Over time, the central outflows will heat more of the surrounding gas, reducing the inflow and allowing the system to settle into a quieter phase. Eventually, the balance will tip again, cooling will dominate, and the process will resume. In this sense, the feeding of the black hole and the breathing of the cluster are linked. The entire system functions as a single organism, inhaling and exhaling matter and energy on timescales of tens of millions of years. On human scales, this cycle is invisible, but in the cosmic record it defines the life of clusters. The feeding of Phoenix A illustrates how a black hole, though small compared to the galaxy it inhabits, can control the thermal history of an environment hundreds of thousands of light years wide. It also shows how deeply interconnected the cosmos can be. An atom that cools in the cluster's outer halo may one day spiral into a black hole's gravity, well contribute to a jet, and then reappear as heated plasma far from where it began. Energy and matter circulate endlessly, driven by the unseen gravity of the giant at the core. In this way, Phoenix A sustains itself not through steady stillness, but through an eternal exchange of inflow and outflow, cooling and heating, silence and eruption. At the center of Phoenix A, the feedback loop that governs the life of the cluster operates like a cosmic engine running on alternating phases of release and restraint. Every component of the system, the cooling gas, the accretion disk, the jets, and the surrounding plasma, participates in this self-regulating cycle. In physical terms, feedback means that the black hole's energy output responds to the rate at which it receives fuel. When the inflow of gas increases, the black hole brightens and its jets strengthen, injecting more energy into the cluster's core. That added energy heats the surrounding gas, reducing the rate of cooling and cutting off the black hole's fuel supply. When the gas cools again, inflow resumes and the process restarts. This feedback mechanism prevents unchecked cooling that would otherwise turn the entire cluster core into a burst of star formation. In Phoenix A, this mechanism functions at the most powerful scale ever observed, a natural experiment in how the universe maintains balance between extremes. The bursting heart of feedback reveals itself through the structure of the cluster's core. X-ray maps show cavities where the gas has been pushed aside, surrounded by bright rims of compressed material. These rims mark the boundaries where jets from the black hole have ploughed into the surrounding plasma, transferring energy through shock waves. The shocks are not violent explosions in the human sense. They move outward at only a few thousand kilometers per second, but across distances of hundreds of thousands of light years their influence is immense. The passage of these waves stirs turbulence and spreads heat, raising the temperature of the intracluster medium just enough to slow its collapse. The energy deposited in this way is enormous, sufficient to reheat billions of solar masses of gas and keep it suspended in a quasi-stable state. Yet even this power does not completely halt cooling in Phoenix A. Observations show that while the outer regions remain hot, dense filaments near the center continue to condense, feeding both star formation and accretion. The black hole's feedback moderates the system but does not fully dominate it. In many clusters, feedback operates quietly with low-level jets and small cavities that appear intermittently over long timescales. Phoenix A is different. The power of its outbursts, the size of its cavities, and the intensity of its X-ray emission all point to a system near the upper limit of what physics allows. The jets carry such momentum that they pierce through the hot gas and continue outward, inflating bubbles that rise buoyantly through the cluster's atmosphere. As these bubbles ascend, they drag cooler gas behind them, creating filaments that glow faintly in optical light. This motion helps to mix the cluster's core distributing metals and heat more evenly. The mechanical work done by the jets not only offsets cooling, but also maintains the structure of the cluster's magnetic field, which threads the plasma like invisible scaffolding. The feedback process thus shapes both the thermodynamics and the geometry of the environment, giving the Phoenix cluster its distinctive layered appearance. Within the nucleus, the accretion disk acts as the control valve of this system. When the inflow of gas becomes denser, the disk grows brighter and more turbulent, releasing jets that erupt along its rotational axis. These jets are powered not only by the gravitational energy of the accreting gas, but also by the spin of the black hole itself. Magnetic fields anchored in the disk extract rotational energy from the event horizon, converting it into kinetic power. This mechanism, known as the Blandford-Znajek process, may be what allows Phoenix A to sustain its immense output for millions of years without exhausting its fuel supply. The jets carry energy outward as beams of relativistic particles that eventually slow, expand, and merge into the surrounding plasma. As they decelerate, they release their energy to the environment, maintaining the pressure balance that stabilizes the cluster's core. The consequences of this feedback extend beyond heating. The turbulence generated by rising bubbles and propagating shocks changes how matter behaves within the cluster. It prevents gas from settling smoothly into the center, instead stirring it into eddies and waves. This motion slows the rate of condensation and keeps the plasma mixed, ensuring that metals and heavier elements produced by supernova in member galaxies are distributed throughout the cluster. Without such mixing, these elements would sink toward the center, leaving the outskirts depleted. The feedback thus acts as a stirring mechanism, maintaining chemical homogeneity on cosmic scales. In Phoenix A, this mixing may also help explain why the cluster remains luminous. Across so many wavelengths, the metals scattered through the gas increase its ability to cool in some regions, while being reheated in others, sustaining the system's perpetual motion. One of the remarkable features of Phoenix A's feedback is its apparent stability despite its intensity. The jets remain roughly aligned over time, implying that the black hole's spin axis does not vary dramatically. This consistency allows the cavities and bubbles to form in a predictable pattern, producing symmetrical features visible even at great distances. Still, minor deviations are present. Some cavities appear slightly tilted, and faint extensions suggest that earlier outbursts may have occurred along different directions. These small shifts reveal that the system evolves subtly, responding to the complex interplay between inflow magnetic fields and rotation. Each eruption writes a new layer into the cluster's structure, like the rings of a tree recording its history. The effectiveness of feedback can be assessed by comparing heating rates to cooling rates. In Phoenix A, the mechanical power of the jets roughly equals the rate at which the gas would otherwise lose energy through radiation. This balance is a delicate one. If feedback were significantly weaker, cooling would dominate, triggering a burst of star formation that could consume much of the available gas. If it were stronger, the gas would become too hot and too diffuse to form stars at all. The observed coexistence of both star formation and active feedback in Phoenix A suggests that the system hovers near equilibrium, oscillating around a narrow range where heating and cooling compete continuously. This oscillation may define the cluster's long-term stability, ensuring that neither process fully suppresses the other. From a cosmic perspective, feedback of this kind represents nature's most efficient form of energy management. A single object smaller than the solar system controls the temperature and structure of an entire region, spanning hundreds of thousands of light years. The Phoenix cluster demonstrates this balance vividly. Its black hole acts as a thermostat for the universe's largest bound structures, switching on and off in response to the conditions it helps create. Each outburst reheats the gas, each period of calm allows cooling to resume, and the two processes together shape the cluster's destiny. The visible structures, the X-ray cavities, the glowing filaments, the steady jets, are the signatures of this vast balancing act. They are not anomalies or eruptions in isolation, but manifestations of an ongoing dialogue between matter and gravity. The bursting heart of feedback within Phoenix A embodies both power and precision. It keeps the cluster alive in a dynamic equilibrium where change is constant but catastrophe is avoided. The feedback process ensures that the black hole never starves and that the cluster never freezes. Through cycles measured in tens of millions of years, the system breathes inflow, ignition, expansion, and calm. The same process that could destroy the cluster instead sustains it, dispersing energy through shock and turbulence, then drawing matter back inward again. In the quiet depths of space, the black hole at the center of Phoenix A continues to pulse an unseen rhythm that maintains the balance between creation and collapse across one of the most powerful systems ever observed. Amid the heat turbulence and outflows that define the Phoenix cluster, a quieter but equally extraordinary process unfolds: the rapid birth of stars in the very region where star formation should be least likely. In most galaxy clusters, the central galaxy remains a place of old stars and dim light, its gas kept too hot to condense by the energy of the resident black hole. Yet in Phoenix A, the situation defies that pattern. Here cooling proceeds at a remarkable rate, and the gas that escapes the grip of feedback condenses into vast clouds, dense enough to collapse under their own gravity. The result is one of the most intense bursts of star formation ever recorded in a central cluster galaxy, a process that converts hundreds of solar masses of gas into stars each year. This rate rivals that of young galaxies in the early universe, but Phoenix A is not young. It is ancient, massive, and embedded in a system already long formed. That such vigorous stellar birth occurs in such a mature environment reveals how deeply the balance between heating and cooling has been disturbed. The signs of this activity appear across the spectrum. In ultraviolet light, the core of Phoenix A shines with the unmistakable signature of hot, newly formed stars. In the infrared, dust warmed by their radiation glows faintly, tracing the cold regions where stars continue to form behind thick veils of gas. Optical images reveal filaments of blue light clusters of young stars strung along the paths once traced by cooling flows. These filaments follow the same general directions as the cold molecular streams observed in millimeter wavelengths, confirming that star formation is proceeding within the same material that feeds the black hole. The two processes, accretion and star birth, occur side by side, drawing from the same reservoir of cooling gas. This coexistence marks a delicate and temporary moment in the cluster's history, a phase when the system's feedback has not yet restored thermal balance. The presence of such star formation challenges long-standing assumptions about the role of black hole feedback. In most clusters, active nuclei inject enough energy to keep their gas reservoirs hot, suppressing new stars. Phoenix A demonstrates that when cooling is strong enough and gas flows dense enough, feedback can lag behind, allowing some material to escape reheating and collapse into stars before being swept away. The balance between these competing processes is narrow, and the Phoenix cluster appears to be caught exactly at that tipping point. Observers estimate that its central galaxy forms stars at a rate exceeding 700 solar masses per year, compared to only a few per year in typical brightest cluster galaxies. The scale is staggering. In 1 million years, enough material converts into stars to match the mass of several entire spiral galaxies. This stellar surge does not occur uniformly. Most new stars form within elongated filaments and knots regions, where cold molecular gas has gathered into dense clouds. These clouds extend for tens of thousands of light-years, curving through the core like luminous threads. Their temperatures are only a few tens of degrees above absolute zero, yet within them gravity compresses hydrogen into the dense clumps that eventually ignite nuclear fusion. Many of these filaments align with the edges of X-ray cavities, implying that the rising bubbles of hot plasma may help trigger their formation. As the cavities expand, they lift cooler gas outward, where it can cool more efficiently, fragment and form stars. Thus, even the black hole's outbursts, though primarily sources of heat, indirectly contribute to new star formation. In Phoenix, a feedback is not simply destructive. It participates in the recycling of matter from plasma to dust to stars and back again. Spectroscopic studies reveal the diversity of this stellar population. The young clusters emit bright ultraviolet radiation, while older populations in the same region contribute a background of redder light. Together they form a composite spectrum that records multiple generations of star birth, suggesting that this activity has been sustained for tens of millions of years. Some stars are massive and short-lived, destined to end as supernovae that will enrich the surrounding gas with heavier elements. Others are smaller and will persist for billions of years, embedding the memory of this period into the long future of the galaxy. The continuous interplay between formation and feedback ensures that the environment never settles completely. Each new star adds to the complexity of the cluster's evolution, releasing radiation and winds that influence the same gas that created them. The coexistence of a powerful active nucleus and a flourishing stellar nursery within the same galaxy is rare but not entirely paradoxical. Both phenomena arise from an abundance of cold gas. When enough material condenses from the cluster's atmosphere, part of it flows inward to feed the black hole, while part collapses under self-gravity to form stars. The division between these two fates depends on local conditions, pressure density and turbulence, and may shift over time as feedback reshapes the gas. In Phoenix A, those conditions currently favor both outcomes at once, resulting in a system that radiates across the spectrum X-rays from the hot gas radio waves, from the jets, infrared from dust, and optical light from young stars. The combination makes the cluster's core one of the most luminous known objects in the nearby universe. The effect on the galaxy's appearance is striking. While most brightest cluster galaxies display a smooth, featureless glow, Phoenix A exhibits subtle structure, wisps, knots, and color gradients that betray the presence of young stellar populations. The central region, typically dominated by old red stars, shows patches of blue where recent formation is most intense. Dust lanes cut through the inner light, indicating that cold material continues to circulate even within the immediate vicinity of the nucleus. Infrared maps show concentrations of warm dust arranged in rings and arcs, likely heated by the combined effect of star formation and nuclear radiation. These features, faint but distinct, turn the otherwise featureless elliptical into a living laboratory of galactic evolution. The consequences of such an episode are far-reaching. A burst of star formation at this scale will alter the mass-to-light ratio of the galaxy, change its chemical composition, and eventually enrich the cluster's gas with metals when massive stars die. Over time, supernova explosions from these new stars will return material to the intra-cluster medium, where it may once again cool and feed the black hole, closing the feedback loop. Thus, Phoenix A's current state may not be a brief anomaly, but part of a repeating cycle in which cooling star formation and feedback occur in alternating dominance. The black hole heats the gas until cooling resumes, cooling forms stars until feedback intensifies again, and the sequence continues across tens of millions of years. To astronomers, Phoenix A's simultaneous starburst and nuclear activity offer a glimpse of processes that were once common in the early universe, when massive galaxies grew rapidly, while their central black holes accreted at high rates. The Phoenix cluster, though far closer in time, behaves like a relic of that earlier cosmic era. Its intense star formation is a reminder that under the right conditions, even the most massive and evolved systems can reawaken, converting their cooling gas into new light. The galaxy's core, filled with young stars shining through veils of dust, stands as an island of renewal amid the surrounding sea of ancient quiescent systems. In the slow rhythm of cosmic evolution, the surge of star formation in Phoenix A will fade as the available gas is consumed or reheated by the next round of feedback. The present luminosity marks only one phase in an endless cycle of condensation and dispersal. Yet while it lasts, this phase illuminates the complex balance that defines galaxy clusters, a balance in which the power of a black hole and the quiet persistence of starbirth coexist, each shaping the other. In the heart of the Phoenix cluster, where heat and gravity wrestle for control, stars are born not in peace, but in the shadow of one of the universe's most powerful engines, a reminder that even in places governed by extremes, creation continues. The inner structure of the Phoenix cluster, when examined through multiple wavelengths, reveals an intricate web of cavities, filaments and clouds that together describe the ongoing interaction between the black hole and its surroundings. The picture is not one of chaos, but of ordered complexity, a visible record of how energy moves through matter across enormous scales. The cavities first traced in X-rays outline where the hot gas has been displaced by jets from the central black hole. Around these voids, long cold filaments twist and curl like smoke caught in a gentle current. Together they form an ecosystem of feedback where energy and cooling, motion and stillness coexist in equilibrium. Mapping these structures has allowed astronomers to understand both the geometry of the outflows and the precise way in which the cluster's atmosphere responds to them. High-resolution images from the Chandra X-ray Observatory reveal that the cavities extend symmetrically from the center of Phoenix A, aligned roughly along the same axis as the radio jets. Each cavity measures tens of thousands of light-years across its edges, sharply defined against the glowing background of hot plasma. These are regions of lower density and pressure carved by outbursts that have pushed aside the intra-cluster medium. In 3 dimensions, they likely resemble ellipsoids or irregular bubbles. Their interiors are not empty. They are filled with relativistic plasma emitting faint radio waves, the afterglow of the jets that created them. When combined with data from radio telescopes, the cavities and lobes align perfectly, confirming that they are the same physical entities viewed through different lenses of the spectrum. The energy required to form each cavity is extraordinary, equivalent to the simultaneous detonation of trillions of supernovae, yet the process unfolds quietly over millions of years. The cavities do not rise alone. Around them are networks of filaments, narrow thread-like structures that glow in optical and infrared light. These filaments contain gas that has cooled from the hot phase into molecular form, its temperature now only a few tens of degrees above absolute zero. They stretch outward from the core, sometimes connecting to the rims of the cavities, as though drawn upward by the bubble's ascent. Their appearance is delicate, but they contain vast amounts of mass, sometimes millions of times that of the Sun. Observations with the Atacama Large Millimeter Array have detected carbon monoxide and other molecules within them, confirming their cold nature and revealing that they serve as pathways for gas flowing through the cluster's central region. Some filaments appear to be falling inward, feeding the nucleus, while others may be uplifted by the jets themselves. The dual motion both toward and away from the center illustrates how feedback redistributes matter without destroying it. Optical imaging from the Hubble Space Telescope adds more detail to this picture. The filaments emit faint hydrogen alpha light, a glow produced when electrons recombine with protons in ionized gas. This emission outlines the contours of cooling flows, tracing the routes along which material condenses from the intracluster medium. In many cases, the filaments appear to wrap around the edges of the X-ray cavities, suggesting that as the bubbles rise, they pull cooler gas outward. Once removed from the intense heat of the core, this gas can cool more rapidly, fragmenting into smaller clumps that may later fall back and restart the cycle of accretion. The geometry of these structures, circular arcs, radial streaks, and spiraling trails, records the combined effects of buoyancy, magnetic tension, and turbulence. No single process dominates. Rather, each contributes to the dynamic texture that defines Phoenix A's heart. Mapping these patterns requires more than imaging. Spectroscopic studies provide the velocity of the gas within the filaments, allowing astronomers to measure their motion along the line of sight. Some streams move inward at hundreds of kilometers per second, while others drift outward more slowly. This complex motion shows that the gas is not static, but circulates in loops rising and falling, like air in a planetary atmosphere. The filaments are supported by magnetic fields which prevent them from dispersing despite the surrounding heat. Without this magnetic confinement, they would evaporate quickly into the hot plasma. Instead, they persist for millions of years, their internal structure stabilized by invisible threads of magnetism. These same fields help channel energy from the jets, guiding the flow of relativistic particles and maintaining the alignment of the cavities over time. Infrared and submillimeter data reveal even more hidden mass. Beneath the visible filaments lie dense clouds of dust that absorb starlight and re-radiate it as thermal emission. This dust traces the coldest, most shielded regions of the cluster's core. Some of it may have formed from the remains of dying stars within the central galaxy, while some may be created as gas cools and condenses. Its presence emphasizes that despite the extreme heat of the surrounding medium regions of deep cold, still exist only a few thousand light-years from the black hole. The coexistence of matter at such different temperatures, from tens of millions of degrees to just a few tens above absolute zero, illustrates how diverse the cluster's internal environment has become. The feedback cycle allows both extremes to persist, maintaining a spectrum of conditions that span the full range of astrophysical processes. When viewed as a whole, the cluster's core resembles a three-dimensional tapestry of energy and matter. Cavities mark where power has erupted outward. Filaments trace where matter has cooled and fallen inward. Between them lies the intermediate phase of warm gas glowing faintly in optical emission lines and linking the two extremes. Each layer tells part of the story: heat expanding, gas cooling, gravity reclaiming, and energy rising again. The structures are not static relics, but active participants in the cluster's life, evolving as feedback continues. Over time, the cavities rise farther from the center, losing energy to the surrounding gas. New cavities form closer in their formation, driven by the next episode of jet activity. Meanwhile, the filaments shift, some evaporating others, coalescing into new stars or feeding the black hole directly. The geometry of the system, mapped through years of observation, provides a record of time written in space. Older cavities lie farther from the center. Newer ones, smaller and brighter, sit nearer to the nucleus. Their distribution indicates multiple cycles of outburst, each separated by tens of millions of years. The alignment of successive cavities suggests that the black hole's spin has remained steady across these episodes, maintaining a consistent direction for its jets. This steadiness contributes to the stability of the cluster, preventing random reorientation that could scatter energy unevenly. It also implies that the inflowing gas, the material that feeds the black hole, carries angular momentum aligned with the existing spin, preserving the system's coherence. Astronomers continue to refine these maps using increasingly sensitive instruments. Each new observation reveals smaller cavities, fainter filaments, and more subtle ripples in the gas. Together they provide a complete picture of how energy moves from the smallest scales of accretion to the vast distances of the cluster's halo. The cavities, acting as conduits of feedback, transfer the black hole's power outward, while the filaments carry mass inward, closing the loop. Their coexistence proves that the feedback process is not destructive but cyclical, maintaining the cluster's structure through a delicate exchange of energy and matter. From a distance, the Phoenix cluster appears serene, a stable island of galaxies suspended in the dark. Up close, its core reveals constant motion cavities, expanding filaments curling and waves of heat rippling through the plasma. Each map, each layer of light captures a different stage of this cosmic dialogue. The cavities are the lungs of the cluster exhaling energy. The filaments are its veins drawing material back toward the heart. Together they sustain one of the most remarkable systems ever observed, a dynamic balance of expansion and contraction, heat and cold, power and stillness, all centered on a single unseen black hole whose influence extends across 500,000 light-years. At the heart of Phoenix, beyond the veils of gas, dust and starlight, lies the object responsible for all the cluster's motion and structure, a supermassive black hole of extraordinary mass. Its direct image remains beyond the reach of current telescopes, hidden by layers of hot plasma and interstellar debris. Yet its presence is written unmistakably in the movement of surrounding stars and gas. To measure its scale, astronomers must rely on indirect evidence: the velocities of orbiting material, the temperature and pressure of the inner plasma, and the power of the jets that emerge from the nucleus. These indicators together reveal an object whose mass approaches several billion times that of the Sun, a gravitational anchor strong enough to bind the innermost region of a galaxy that itself outweighs the Milky Way by an order of magnitude. This invisible mass defines the potential well into which the cluster's cooling gas continually descends. Its horizon, the event boundary where light itself can no longer escape, spans only a few times the diameter of the solar system, yet it controls the fate of matter and energy across hundreds of thousands of light years. Estimating the mass of such an object requires meticulous observation. Optical spectra reveal that the stars within the inner few thousand light-years of Phoenix A move at velocities exceeding 1,000 kilometers per second. These speeds cannot be sustained by the galaxy's visible matter alone. The gravitational potential implied by such motion demands a central object of immense density. Using established dynamical models, astronomers infer a black hole mass in the range of billions of solar masses. Independent confirmation comes from modeling the energy output of its jets and cavities. The total mechanical power release corresponds to what a black hole of similar mass could supply, given a realistic efficiency of accretion. Even with uncertainties in geometry and inclination, all lines of evidence converge on the conclusion that Phoenix A harbours one of the most massive active black holes known in the nearby universe. To visualize its size is to grasp the scale of extremes. The event horizon, the point of no return, might be about 30 billion kilometers across, comparable to the orbit of Neptune around the Sun. Beyond that lies the accretion disk extending outward for perhaps a few light days. This disk, though minuscule compared to the galaxy, emits radiation and drives jets that affect the entire cluster. Surrounding it is a vast envelope of ionized gas and dust, known as the circumnuclear region, where magnetic fields twist the flow into complex shapes. Each layer contributes to the process by which gravity becomes light and light becomes motion. The gravitational well of Phoenix A is so deep that time itself flows measurably slower near its horizon than in the wider cluster. Matter falling inward spirals at relativistic speeds, releasing torrents of energy that sustain the feedback cycle described in earlier sections. Astronomers distinguish between the radiative luminosity of the accretion disk and the mechanical luminosity of the jets. In Phoenix A, the latter dominates. The black hole's output is directed primarily into kinetic form, launching particles and magnetic fields outward rather than emitting light. This difference explains why, despite its power, the nucleus does not appear exceptionally bright in optical wavelengths. Most of its energy leaves as motion, not radiation. The efficiency with which it converts gravitational potential into jet power approaches theoretical maxima predicted by general relativity for a rapidly spinning black hole. Such a high spin rate implies that the black hole has grown through coherent accretion material falling in roughly aligned with its rotation, rather than through random mergers. Over time, this alignment stabilizes the orientation of the jets, producing the long straight cavities observed in X-ray maps. Understanding the scale of Phoenix A's black hole also sheds light on the evolution of galaxies and clusters. In less massive systems, feedback from black holes tends to shut down star formation by heating gas beyond its cooling threshold. In Phoenix A, the sheer size of the central object allows it to modulate that process on a grander scale. Its gravity ensures that even after powerful outbursts, gas eventually returns, feeding both new stars and renewed activity. The black hole acts not as a terminator of growth, but as a regulator, establishing a dynamic equilibrium between heating and cooling. The ratio between its mass and that of its host galaxy follows the same proportionality observed elsewhere in the universe, roughly 1 part in 1,000, confirming that even at such extremes cosmic systems obey familiar rules. Yet Phoenix A stretches those rules to their limit, revealing what happens when feedback cooling and accretion all operate near their theoretical boundaries. The region immediately surrounding the black hole is a place of physical conditions unattainable anywhere else. Magnetic fields thousands of times stronger than those on Earth channel plasma into collimated streams. Temperatures in the inner disk rise to millions of degrees, and particles accelerated in the jets reach energies far beyond what human instruments can produce. Space and time themselves are distorted by the black hole's gravity. Light bends around it, creating a sphere of apparent brightness that would be visible if the inner region could be resolved. For now, such resolution remains the domain of theoretical modelling, but future instruments, perhaps combining very long baseline interferometry at higher frequencies, may eventually glimpse the shadow of Phoenix A's event horizon, as was done for other nearby black holes. If that happens, it would confirm directly what is now inferred indirectly, that at the core of this luminous cluster sits a rotating singularity of spacetime quietly dictating the rhythm of galaxies. Despite its dominance, the black hole's gravitational reach is finite. Beyond a few thousand light-years, the mass of the surrounding stars and gas becomes comparable, and the galaxy's collective gravity takes over. Yet the influence of the nucleus extends far beyond that physical limit because energy released there propagates outward through the cluster. This coupling between the smallest and largest scales is one of the most profound insights gained from studying Phoenix A. It shows that an object no larger than a planetary system can shape structures measured in millions of light years. The mechanics of that, coupling the conversion of gravitational energy into mechanical work, lie at the heart of astrophysical feedback and help explain why the universe's largest structures remain stable. To quantify the black hole's impact further, astronomers calculate the binding energy of the surrounding gas and compare it to the energy released by recent outbursts. In Phoenix A, the latter exceeds the former, meaning that the black hole could in principle unbind the entire core if its output were concentrated rather than distributed. The fact that the cluster remains intact indicates that feedback is finely tuned. Energy is released gradually and spread efficiently, avoiding catastrophic disruption. This balance underscores the precision with which natural systems self-regulate. Even at maximum power, the black hole does not destroy its environment. It sustains it through cycles of controlled release. The scale of the black hole in Phoenix A invites reflection on the broader architecture of the cosmos. Such giants are not rare in clusters, but few are so active or so well studied. Their presence reminds astronomers that the universe's most massive objects are also its most delicate regulators, capable of both destruction and preservation. Phoenix A's black hole, operating at the edge of known energy scales, exemplifies this duality. It is at once an engine of chaos and an agent of order, a gravitational well that consumes matter, and a fountain of energy that keeps the cluster alive. In the silent depths of intergalactic space, its influence extends far beyond its size, defining the structure, temperature, and evolution of one of the most luminous clusters ever observed. Its scale is not measured only in mass or distance, but in the reach of its gravity, a reach that binds the galaxies of the Phoenix cluster together and marks the center of one of the universe's grandest cosmic systems. To describe Phoenix A as the most powerful known black hole requires not only observing its behavior, but also comparing it against others that occupy similar positions across the universe. Astronomers define power in specific physical terms, the rate at which energy is transferred or released. For black holes, this energy can appear as light from the accretion disk, as kinetic energy in jets, or as mechanical work done on the surrounding gas. Each mode leaves a distinct signature, and by measuring those signatures across many systems, researchers can rank the relative strength of their central engines. In Phoenix A, the evidence lies in the scale of the cavities, the temperature and pressure of the surrounding plasma, and the motion of the gas in its core. These indicators together imply a mechanical power output far greater than that of any comparable object, rivaling the combined luminosity of entire clusters of galaxies. The first benchmark for such comparisons is radiative luminosity. Quasars powered by rapidly accreting black holes can emit energy equivalent to trillions of suns, their light visible across billions of light years. Yet this brilliance represents only one form of power: electromagnetic radiation. Many black holes, including the one in Phoenix A channel, most of their energy into jets and outflows rather than visible light. To account for this, astronomers use the concept of total energy output, or jet power, derived from the cavities and shocks those outflows create. In typical active galaxies, jet power ranges between 10 to the 44 and 10 to the 45 watts. Phoenix A surpasses 10 to the 46, placing it in a category that extends beyond even the most energetic quasars. Its central engine operates in a regime where mechanical energy dominates, transferring momentum and heat directly into the surrounding medium rather than radiating it away. Comparing power between systems requires normalization. Black holes differ in mass accretion rate and spin, all of which affect their efficiency. Scientists therefore use dimensionless ratios such as the Eddington fraction, the proportion of a black hole's energy output to the theoretical maximum it can sustain without blowing away its accreting material. In Phoenix, estimates suggest that the nucleus operates at a fraction of this limit, perhaps only a few % yet, because the black hole itself is so massive, even this small fraction corresponds to extraordinary absolute power. It is as if a slow-burning furnace of immense size produces more heat than a smaller one burning at full blaze. This efficiency, combined with sustained activity over millions of years, gives Phoenix A its unmatched influence on its environment. To put its magnitude in perspective, astronomers compare it with other famous systems. The black hole in the galaxy M87, for example, has long been studied as a standard for powerful jets. Its cavity power measures roughly 10 to the 45 watts, impressive, but still an order of magnitude below Phoenix A. Similarly, the black hole in the Perseus cluster, known for its rippling X-ray waves, generates a power output several times smaller. Even the brightest quasars, whose disks shine across the visible universe, distribute much of their energy as radiation rather than mechanical force. Phoenix A stands apart because of the sheer mass of gas it moves and the distance across which its influence extends. It does not rely on visible brightness. Its authority is written in motion and structure, not light. Another metric used for comparison is the enthalpy of the cavities, the total thermal and kinetic energy stored within them. By measuring the volume and pressure of the displaced gas, researchers estimate how much energy must have been injected to form them. For Phoenix A, this energy reaches levels that challenge conventional models of black hole accretion. To sustain such outbursts, the black hole must either spin rapidly or accrete matter with exceptional efficiency. Observations suggest that both may be true. The jets maintain a stable orientation, implying a coherent magnetic field aligned with the spin axis. The consistency of this orientation over multiple outbursts supports the idea of a long-lived, highly spinning black hole, a cosmic dynamo converting rotation into power. Astronomers also consider timescale. Some systems produce brief, intense flares of energy that fade quickly. Phoenix A's activity, however, endures for millions of years. The cavities rise slowly through the intra-cluster medium, evidence that the outbursts have persisted over long durations. This sustained energy release differentiates Phoenix A from transient sources like gamma-ray bursts or supernovae, whose energies, though immense, act on short timescales. The black hole's consistency allows it to reshape the cluster gradually, rather than explosively, preserving its structure while maintaining thermal balance. In this sense, its power is both vast and disciplined, a continuous influence rather than a singular event. When comparing across cosmic history, Phoenix A also serves as an analogue for conditions in the early universe. During the epoch when galaxies and quasars were forming rapidly supermassive black holes, may have driven outflows of similar magnitude regulating star formation on galactic scales. Today, such extreme systems are rare. The Phoenix cluster thus provides a window into how those ancient feedback processes operated. Its mechanical power, measurable and sustained, mirrors the hidden mechanisms that once governed galaxy evolution billions of years ago. By observing Phoenix A, astronomers effectively study a modern echo of the universe's most formative period. Quantifying power extends beyond numbers. It involves understanding how energy couples to matter. A black hole's output can heat gas, compress it, or expel it entirely depending on conditions. In Phoenix A, the coupling is efficient but not destructive. The jets deposit their energy, gradually allowing the gas to expand without being blown away. This fine balance is what makes the cluster's core stable despite continuous agitation. The relationship between the cavity power and the radiative cooling rate defines whether the system will remain in equilibrium. In Phoenix A, those two rates are comparable, meaning that the energy released by the black hole nearly equals the energy lost through radiation. This equilibrium keeps the cluster from either collapsing under cooling or dispersing under heating. These comparisons highlight that most powerful is not a claim of transient brilliance, but of cumulative influence. Over tens of millions of years, the energy injected by Phoenix A exceeds the total energy output of countless galaxies combined. Its influence shapes not only the cluster's structure, but also its long-term evolution. The surrounding plasma remains hot because of it. The rate of star formation, though high, is moderated by it, and the motion of gas across hundreds of thousands of light years follows patterns determined by its feedback. No other known system shows such a clear, measurable connection between a single black hole and an environment of this scale. In scientific literature, Phoenix A has become the reference point for studying high-power feedback. It bridges the gap between luminous quasars where radiation dominates and radio-loud clusters where mechanical energy rules. Its combination of massive scale, sustained output, and clear observational signatures makes it the benchmark against which future discoveries are compared. The black hole's title as most powerful is not an exaggeration of brightness, but a literal measurement of energy transfer supported by data across multiple wavelengths and confirmed by independent studies. In the quiet depths of the Phoenix cluster, hidden behind veils of gas and light years of distance, the universe demonstrates its capacity for controlled intensity. Phoenix A stands not as a fleeting outburst, but as a continuous furnace of gravitational energy, one whose power measured against all others defines the upper limit of what black holes can do. After every eruption from the central black hole, the Phoenix cluster settles into a phase of uneasy quiet. This calm is not stillness, but a slow realignment, a period when the heated gas expands. The shock waves fade and the balance between cooling and heating re-establishes itself. Each outburst leaves behind a landscape of bubbles, filaments and ripples that continue to move long after the jets themselves have quieted. The cavities drift outward, like rising smoke carrying energy into the cluster's outskirts. Behind them, new material begins to cool again, condensing toward the center to feed the next cycle. The apparent calm is thus a preparatory stage, a reset in the cluster's breathing, when inflow and outflow momentarily reach equilibrium, before tipping once more toward instability. During this interval, the cluster's X-ray glow smooths into a near-uniform halo. The strong pressure gradients that mark the active phase begin to soften and turbulence in the inner regions gradually decays. Gas motion slows the filaments settle, and the sound waves from the last shock propagate outward into the vast, thin plasma that fills the cluster's body. Observations show that the central temperature stabilizes hovering between 20 and 30 million degrees Celsius, hot enough to emit X-rays, but cool enough that radiative losses continue. The rate of energy loss through radiation, known as the cooling rate, is the silent counterpoint to the black hole's mechanical power. As radiation escapes the gas in the densest regions, loses pressure, and drifts inward, restarting the cycle. This gradual inward flow is invisible in most images, but spectral lines betray its presence. They reveal gas moving toward the center at hundreds of kilometers per second, carrying with it the seeds of the next outburst. As the gas accumulates, its density rises, forming reservoirs of cold molecular material detected in millimeter wavelengths. These clouds become the source of both star formation and accretion. The balance between the two depends on subtle differences in density. An angular momentum gas that forms clumps collapses into stars, while gas that remains diffuse spirals inward to feed the black hole. In Phoenix, both processes continue, even in the so-called calm phase, although at reduced intensity. The feedback engine never truly stops. It only cycles between loud and quiet states. The timescales of these transitions are immense. A single feedback cycle from the onset of an outburst to the decline into quiescence and the rise of the next may span tens of millions of years. Yet on that scale, the Phoenix cluster has undergone many such oscillations since its formation. Each leaves behind evident concentric shells of gas-aged radiolobes and cavities now faded with distance. When astronomers measure the ages of these features, they find consistent intervals confirming that the cluster's heartbeat follows a steady rhythm. The calm phases are not rare pauses but essential parts of its long-term regulation. They allow energy to redistribute evenly, preventing local overheating that could unbind the cluster's atmosphere. The return to equilibrium after an eruption depends heavily on the cooling rate of the plasma. As hot gas radiates, it becomes denser and sinks toward the center, but magnetic fields resist compression, shaping the flow into narrow channels. These magnetic filaments act as safety valves, guiding cooling material away from the most unstable regions. Their persistence during quiet phases demonstrates that magnetic structure once established endures for millions of years. It maintains coherence even as temperature and density change. The filaments stretching tens of thousands of light years mark the pathways through which matter circulates between the outer halo and the nucleus. From a wider perspective, the calm between outbursts defines the cluster's visual character. In this phase, the Phoenix cluster resembles a faint, nearly spherical glow with only gentle gradients in brightness. The dramatic cavities are still present but softened by distance and diffusion. The jets fade into ghostly radiolobes, relics of the black hole's earlier fury. Infrared maps show faint warmth from residual dust, heated by recent star formation, while optical light reveals only the faintest traces of new stellar clusters. To a distant observer, the cluster seems peaceful, unaware of the turmoil that will eventually return. This deceptive serenity underscores the stability of the feedback process, a system powerful enough to disturb an entire cluster, yet restrained enough to allow it to recover. The calm phase also provides an opportunity for astronomers to study the cluster's microphysics in detail. Without the confusion of fresh outflows, the gas can be examined for signs of conduction diffusion and turbulence decay. Measurements show that conduction transfers heat from outer hotter layers to inner cooler ones, helping to prevent rapid collapse. The rate of conduction depends on the strength of magnetic fields, which can either facilitate or suppress heat flow depending on their orientation. The interplay between conduction and radiation determines how long the calm phase lasts before the next episode of instability. In Phoenix A, this interval appears shorter than in most clusters, suggesting that the balance tips back toward activity more quickly here than elsewhere. Star formation during the calm periods never ceases entirely. Pockets of molecular gas continue to collapse quietly, forming small clusters of young stars that populate the galaxy's inner regions. These stars add subtle new light to the otherwise ancient population, creating a spectral signature distinct from most brightest cluster galaxies. When the next outburst begins, many of these young clusters are engulfed in turbulence, spreading their metals and dust through the environment. In this way, even the calm intervals contribute to the enrichment of the cluster's gas, seeding future generations of stars with heavier elements. The longer the black hole remains in a subdued state, the more material accumulates near the core. Eventually, the balance tips once again. As gas density increases, so does the rate of accretion, and with it the release of gravitational energy. The process accelerates until jets reignite, and another outburst begins. This pattern repeats with near-regular cadence, each cycle self-regulating but slightly different from the last. Variations in the inflow rate, the alignment of magnetic fields, or the external pressure of the cluster's atmosphere can all alter the duration and intensity of the next eruption. In Phoenix A, the system's massive scale ensures that even small deviations have enormous consequences, shaping the observable features that telescopes record today. To human perception, these transitions seem frozen, yet they define the life of the cluster as surely as seasons define life on Earth. The calm between outbursts is the cosmic equivalent of winter, a time of recovery, cooling, and quiet build-up before the next cycle of growth and energy release. The Phoenix cluster's long intervals of apparent stillness are thus moments of preparation, when forces unseen begin to gather again. As gas cools and sinks, as magnetic fields stretch, and align the conditions for renewed feedback, assemble silently. The next eruption will come not as a sudden catastrophe, but as the inevitable continuation of a cycle that has governed this system for billions of years. Through these alternating phases, Phoenix A maintains its identity as both destroyer and preserver. The calm between outbursts is the pause that makes the next surge possible, a crucial counterpoint to its power. Without it, the cluster would spiral into either endless heating or catastrophic collapse. With it, the system endures, balanced on the thin boundary between stability and chaos. In that enduring rhythm, eruption, recovery, and repose lies the essence of the Phoenix cluster, a vast structure whose apparent tranquility conceals the pulse of a black hole that never truly rests. Studying Phoenix A and the processes unfolding within its core demands a kind of astronomy that looks far beyond visible light. The most important features of the cluster, its cavities, jets, and filaments, remain invisible to human eyes, hidden in wavelengths that can only be captured by specialized instruments orbiting above Earth's atmosphere or stationed in high, dry deserts. Through these tools, astronomers reconstruct an image of a system no ordinary telescope could see. Each wavelength reveals a different layer of truth. X-rays display the hot plasma radio waves, expose the relativistic jets. Infrared light traces the dust and newborn stars, and optical observations capture the cooler filaments and galaxies embedded within. Together they form a composite portrait of the cluster, allowing scientists to observe phenomena that unfold across scales of temperature, energy, and time unmatched anywhere else in the nearby universe. X-ray observations remain the cornerstone for understanding the Phoenix cluster. The Chandra X-ray Observatory has provided the sharpest images of its hot gas, mapping its temperature, density, and pressure. From this radiation, astronomers identify cavities, ripples, and shock fronts that betray the presence of the central black hole's outbursts. The X-ray light originates from electrons decelerating in the intense gravitational field of the cluster, a process that converts kinetic energy into electromagnetic radiation. Because this emission depends on temperature, the resulting images act as thermal maps, showing how energy moves through the cluster's core. The brightest regions correspond to densest, coolest gas, while darker zones indicate evacuated cavities. These data are not merely pictures, but precise measurements that can be turned into numbers, volumes, pressures, energies, and ages, each quantifying the black hole's influence over time. Radio observations complement this view by tracing the flow of particles ejected from the black hole. Using arrays of antennas spread across continents, astronomers detect the faint synchrotron radiation emitted by electrons spiraling along magnetic field lines. In Phoenix A, these radio structures fill the cavities visible in X-rays, confirming that they are inflated by jets. The radio lobes extend tens of thousands of light years from the center, curving slightly as they interact with the surrounding medium. Their brightness varies along their length, fading as the particles lose energy. This variation allows astronomers to estimate the age of each outburst, providing a timeline that matches the pattern seen in X-ray light. The combination of radio and X-ray data thus offers a three-dimensional picture. The X-rays reveal the displaced gas, and the radio emission fills those voids with the relics of past eruptions. Infrared and submillimeter observations add another dimension by revealing what lies in the shadows of the hot gas. Instruments like the Herschel Space Observatory and the Atacama Large Millimeter Array detect the cold molecular clouds and dust that form stars and feed the black hole. In the Phoenix cluster, this emission is especially bright, indicating massive reservoirs of cold gas concentrated near the core. These data show that the cluster's feedback cycle involves not only heat but also condensation matter falling inward to replenish what has been lost. In wavelengths where heat from young stars glows softly against the darkness, astronomers can trace the filaments that link the cluster's hot and cold regions. They see how the same structures visible in X-rays as cavities reappear in the infrared as streams of cooled gas, proving that both phases belong to the same continuous process. Optical observations, though less dominant, provide essential context. The Hubble Space Telescope captures the light of the galaxies themselves, revealing their orbits and interactions within the cluster. In the case of Phoenix A, the central galaxy displays a faint halo that merges with the surrounding intracluster light. Filaments of hydrogen alpha emission stretch outward from the nucleus, marking regions where gas cools through radiation. These filaments correspond precisely to the paths seen in infrared and radio data, demonstrating how energy flows through every layer of the electromagnetic spectrum. Ground-based observatories using spectrographs measure the velocity of this gas, confirming that it moves both inward and outward, the signature of a feedback cycle caught mid-phase. To integrate these observations, astronomers rely on a technique called multi-wavelength synthesis. Each dataset taken at a different frequency is overlaid on the others, creating a composite that reveals correlations invisible in any single image. Through this approach, the Phoenix cluster emerges not as a collection of disconnected signals, but as a unified system. The cavities seen in X-rays correspond exactly with radio lobes, while the cold filaments of dust and gas align with the rims of those cavities. This consistency confirms that the processes at work, jet inflation, gas cooling, and star formation, are not isolated events, but interconnected parts of a single feedback mechanism. Even with this wealth of information, much remains unseen. The central black hole itself lies beyond direct observation, its event horizon hidden by intervening dust and plasma. The region where its gravitational field becomes absolute can only be studied through modelling and inference. Simulations based on general relativity suggest that matter spirals inward until magnetic pressure and rotation channel part of it outward as twin jets. Observational data from Phoenix A match these predictions with striking precision. The shape of its cavities, the strength of its radio emission, and the pattern of its shocks all agree with models of a rapidly spinning black hole driving relativistic outflows. By comparing these observations with simulations, scientists can infer parameters such as spin rate, magnetic field strength, and efficiency of energy conversion. Phoenix A, though distant, becomes a natural laboratory for testing the physics of extreme gravity. New instruments continue to refine this picture. The James Webb Space Telescope observes the cluster in infrared detail, resolving filaments and dusty regions previously blurred into obscurity. Its sensitivity reveals faint stellar nurseries forming along the cold streams, proving that star formation remains active even in the presence of powerful feedback. Future X-ray missions like Athena will provide higher resolution and broader energy coverage, allowing measurement of gas motion directly through Doppler shifts in spectral lines. With these data, astronomers will map the flow of plasma in 3 dimensions, capturing turbulent shocks and cooling simultaneously. Phoenix A will thus evolve from a case study into a template for understanding all clusters where black holes regulate their environments. The process of observing the invisible is also one of interpretation. Data must be cleaned, calibrated, and compared across instruments, separated by years and by vastly different resolutions. Each observation carries uncertainties, variations in detector sensitivity, cosmic background interference, and the inherent difficulty of projecting 3-dimensional structures onto 2-dimensional images. Despite these challenges, the picture that emerges remains remarkably consistent. The Phoenix cluster radiates power through every band of the spectrum, each wavelength carrying a different aspect of its story. From the hot X-ray plasma to the cold dust and gas from the invisible jets to the luminous stars they help create, every observation confirms that the universe's most powerful forces often reveal themselves not through light, but through the subtle patterns that light leaves behind. In this way, astronomers have learned to read the Phoenix cluster like a palimpsest of energy. Each wavelength is a layer of writing over the last, none erasing the others, but combining to tell a story of gravity, heat, and motion. The instruments that capture these layers, orbiting telescopes, radio arrays, infrared detectors, act as translators between the visible and the hidden. They allow humanity to witness a system that would otherwise remain forever beyond reach. Through them, the invisible becomes measurable, the distant becomes intimate, and the vast machinery of cosmic feedback reveals itself as both knowable and profoundly beautiful. When the Phoenix cluster was first examined in detail, it revived one of astrophysics' most persistent puzzles, the so-called cooling flow problem. In theory, the hot plasma filling a galaxy cluster's core should radiate energy, continuously lose temperature, and condense into cooler gas that forms stars at a high rate. Calculations made decades ago predicted that the centers of massive clusters would turn into prolific star factories, forming hundreds of solar masses worth of new stars every year. Yet for most clusters observed, this expectation failed. X-ray studies revealed that while gas did cool, it rarely condensed in sufficient quantity to match those predictions. The discrepancy implied that some form of heating must counteract the cooling, preventing runaway star formation. For years, astronomers debated what that heating mechanism might be, and the prevailing answer eventually became the feedback from active galactic nuclei, the periodic eruptions of energy from supermassive black holes that reheat the surrounding gas. In most clusters, this explanation fit well feedback roughly balanced cooling, leaving the cores stable and relatively quiet. Then Phoenix A appeared luminous and restless, and the neat balance that theory had established was thrown into question once again. The central galaxy of the Phoenix cluster defied the expected equilibrium. It hosted both an extremely powerful active nucleus and a star formation rate more than 100 times greater than in other similar systems. The X-ray luminosity of its cooling gas was enormous, implying that radiative losses were proceeding faster than the feedback could compensate. At first glance, this contradicted the notion that black hole activity always keeps clusters stable. The cooling flow problem seemed reborn not as a failure of observation, but as evidence that the feedback cycle could falter or become temporarily overwhelmed. Phoenix A provided a living example of that imbalance, a system where cooling star formation and feedback coexist in extreme proportion. To quantify the scale of this mismatch, astronomers measured the cooling rate directly. By examining the X-ray spectrum of the cluster's core, they could determine how much energy the plasma was losing per second, and translate that into a rate of mass condensation. The result approached several thousand solar masses of gas cooling each year enough to sustain the observed burst of star formation and feed the central black hole simultaneously. Yet even this rate was lower than the theoretical maximum predicted by classic cooling flow models, suggesting that some heating still occurred. The key insight from Phoenix A was not that feedback failed, but that it operated intermittently, allowing cooling to surge ahead during its quieter intervals. The system was not broken but out of phase, a dynamic feedback loop caught mid-cycle, momentarily dominated by cooling before the next major outburst would restore balance. This realization reframed the cooling flow problem as a question of timing rather than of mechanism. In most clusters, the cadence of outbursts roughly matches the cooling time of the gas, maintaining a steady equilibrium. In Phoenix A, the gas cools faster than usual, perhaps because the cluster's density is unusually high, or because its magnetic fields and turbulence allow heat to escape more efficiently. As a result, the black hole must work harder and erupt more often to keep pace. The intense cavity power and shock waves observed in its core may represent the system's attempt to catch up a feedback engine, striving to reassert control over a rapidly cooling atmosphere. This cyclical imbalance may explain why Phoenix A is simultaneously the most powerful and one of the most actively star-forming cluster cores ever seen. The cluster's behavior also provides insight into the microphysics of cooling itself. Radiative losses in the intracluster medium depend strongly on metallicity, the abundance of heavy elements such as iron and oxygen that enhance energy emission through line radiation. Observations show that Phoenix A's core is rich in metals, likely produced by countless generations of supernovae within its galaxies. This abundance accelerates cooling, allowing gas to condense more efficiently. At the same time, turbulence from past outbursts mixes hot and cool regions, creating pockets where temperature and density vary dramatically. These fluctuations can promote condensation, forming the cold filaments that thread through the cluster's heart. Thus, the very feedback that should suppress cooling also seeds the conditions that make cooling possible. The Phoenix cluster embodies this paradox. Heating and cooling are not opposing forces but parts of a single self-sustaining process. To test this interpretation, astronomers model the cluster's evolution using computer simulations that incorporate both cooling and feedback. When parameters are tuned to match Phoenix A's observed mass temperature and jet power, The models reproduce many of its features: the large cavities, the long filaments, and the high but transient star formation rate. The simulations suggest that the system is caught in a short-lived phase of heightened activity that will subside once feedback heats the core sufficiently. Over hundreds of millions of years, Phoenix A will likely return to a state more typical of galaxy clusters, where cooling and heating remain balanced. For now, however, it stands at the crest of that oscillation, offering a rare glimpse of what happens when the equilibrium briefly tips toward cooling. The implications of this understanding extend beyond a single cluster. The cooling flow problem, once a discrepancy confined to theory, has become a key to understanding how structure evolves on the largest scales. Feedback from black holes does more than maintain thermal balance. It regulates the growth of galaxies and the distribution of heavy elements in the universe. Without it, clusters would collapse into dense knots of stars and gas, consuming their material too quickly. With it, they remain extended, luminous, and stable over billions of years. Phoenix A, by stretching this balance to its limit, helps define the boundaries of that regulation. It shows that feedback can fail temporarily, but never entirely, that even in its extremes the universe finds ways to restore equilibrium. Observational campaigns continue to refine the details. Measurements of gas motion using spectrometers reveal gentle turbulence rather than violent convection, suggesting that energy spreads through sound waves and slow mixing instead of sudden shocks. The efficiency of this process determines how long it takes for feedback to reheat the core. In Phoenix A, the turbulence appears moderate, implying that cooling will eventually dominate again, unless another powerful outburst intervenes. This pattern, repeated imbalance followed by recovery, may represent the universal rhythm of cluster evolution. In revisiting the cooling flow problem through the lens of Phoenix A, astronomers have come to see it not as a contradiction, but as a sign of life in these cosmic giants. The apparent mismatch between heating and cooling is the heartbeat of a system that never stops evolving. Each pulse of feedback and each surge of condensation marks stages in a dialogue between gravity and thermodynamics. The Phoenix cluster, with its radiant gas and its restless core, offers the most vivid expression of that dialogue yet recorded. It demonstrates that the universe's larger structures are not static, but alive, with cycles of regulation continually adjusting themselves to remain intact. Through Phoenix A, the old puzzle of cooling flows becomes less a problem to be solved and more a story to be understood, one in which the push and pull of energy shape galaxies, stars and clusters across cosmic time. The cluster's extremes remind us that balance in nature is rarely perfect or permanent. It is dynamic, maintained through oscillation rather than stasis. As the feedback engine continues to pulse and the gas continues to cool, Phoenix A carries the imprint of that eternal conversation, illuminating how even the most powerful systems in the cosmos rely on fragile equilibrium to endure. From the outer halo of the Phoenix cluster to the very heart of its black hole, the journey through its layers reveals the universe operating near its physical limits. Every process, gravitational collapse, radiative cooling, magnetic confinement, jet acceleration, and star formation, reaches an intensity rarely observed elsewhere. Phoenix A stands as a kind of natural experiment in cosmic extremity, a place where energy and matter negotiate on the grandest scale possible. The cluster's features, measured across the full spectrum of light, display the full interplay between destruction and creation. The same forces that tear through the gas also sculpt it into new stars. The same eruptions that heat the plasma also redistribute it, preserving the system as a whole. Looking at Phoenix A is like watching a universe within the universe, an isolated theatre where the fundamental laws of physics are written in motion and light. At the largest scale, the cluster extends across millions of light years, its mass amounting to several quadrillion suns. Its gravitational field bends space itself, shaping the paths of galaxies that orbit within its domain. Through gravitational lensing, the cluster distorts the background cosmos, magnifying distant galaxies that lie behind it. These arcs of distorted light act as silent witnesses to the cluster's immense weight, revealing the presence of dark matter that outweighs visible matter by a factor of 5. This dark component, though invisible, forms the framework upon which everything else rests. The hot plasma that glows in X-rays, the galaxies that drift slowly within, and the central black hole all exist within this unseen gravitational web. Phoenix A's power cannot be understood without acknowledging this structure, because every burst of feedback, every cavity and shock takes place inside the larger context of the cluster's gravitational field. Moving inward, the intermediate region of the cluster reveals how energy travels from the center to the periphery. Outbursts from the black hole send waves of sound and turbulence through the gas, carrying heat across hundreds of thousands of light years. These waves, though faint, propagate for tens of millions of years, their ripples recorded as subtle rings in the X-ray glow. They spread energy without violent explosions, maintaining the cluster's stability. In this way, Phoenix A demonstrates how nature favors efficiency. The black hole's power, rather than radiating chaotically, diffuses smoothly through the cluster's atmosphere, ensuring that even such extreme energy serves to preserve structure rather than destroy it. Closer to the core, the geometry becomes more intricate. Cavities rise through the plasma like bubbles in an ocean, dragging with them filaments of cooler gas that stretch and twist as they ascend. These filaments trace the fine balance between gravity's pull and the pressure of heated plasma. They glow faintly in optical and infrared light, connecting the cold reservoirs of star-forming material with the hot surroundings. Magnetic fields thread through them, invisible but vital, providing tension that keeps the filaments intact. Without those magnetic supports, the cooler material would dissipate into the surrounding heat. Each filament, sometimes hundreds of light-years long, represents matter caught between two fates, falling inward to feed the black hole, or escaping outward, lifted by the buoyant rise of the cavities. The cluster's inner region thus becomes a meeting ground, where inflow and outflow coexist, a visible manifestation of cosmic balance in action. At the very center lies Phoenix A's black hole, an object so dense that its gravity defines the limit between the visible and the unknowable. The energy radiated from the accretion disk and expelled through jets originates from this infinitesimal region, where time slows and space curves upon itself. The jets that escape along its poles move at nearly the speed of light, carving through the surrounding gas and forming the enormous cavities observed in X-rays. The scale difference between cause and effect is staggering. An object smaller than the solar system influences matter across distances measured in hundreds of thousands of light years. No human-built engine, no natural process on any planet approaches this efficiency. It is gravity at its most refined, transforming in falling matter into energy that sustains an entire cluster's equilibrium. To comprehend Phoenix A's significance, astronomers compare it not only to other clusters, but also to theoretical models of cosmic evolution. In doing so, they find that this system encapsulates nearly every major process that governs large-scale structure formation. The cluster's dark matter halo defines its gravitational skeleton. The hot intracluster medium acts as the thermal reservoir. The black hole provides feedback that regulates temperature and density. The interplay among these components mirrors the broader evolution of the universe itself: collapse, heating, cooling, feedback, and renewal. Phoenix A, by operating at such extremes, magnifies these universal processes, making them observable within a single object. It becomes both a microcosm and a magnifying lens for cosmic history. The observations gathered from this cluster have reshaped how scientists think about balance in the cosmos. Once feedback was viewed mainly as a stabilizing force, preventing clusters from overcooling. Phoenix A demonstrates that stability can include moments of excess, that the equilibrium between heating and cooling is dynamic, not static. The cluster's current starburst phase and powerful jet activity mark a temporary departure from that balance, yet even this deviation follows predictable physical rules. Over time, the feedback will reheat the gas slow star formation and restore the steady rhythm that has governed the cluster for billions of years. In this cycle, extremes are not failures but necessary oscillations, a reminder that cosmic systems thrive on fluctuation rather than permanence. Beyond its physical importance, Phoenix A also redefines how we perceive energy and scale. Its power output, when converted to familiar terms, dwarfs all known phenomena. Each second its jets release as much energy as our Sun would emit in its entire 10 billion year lifetime. Over the duration of a single feedback cycle, that energy equals the total radiation from all the stars in a galaxy like the Milky Way. Yet the cluster remains serene in appearance, its light diffuse and steady, its changes imperceptible to human timescales. The immensity of its activity contrasts with the calm of its presentation, revealing the quiet grandeur of cosmic power operating beyond ordinary comprehension. The study of Phoenix A continues to deepen as new instruments refine the view. Future X-ray observatories will resolve turbulence in the gas with greater precision, mapping the motions of matter in 3 dimensions. Radio arrays will trace the magnetic filaments and measure the age of the plasma that fills the cavities. Infrared telescopes will observe how the current burst of star formation evolves and fades. Each advancement will reveal another aspect of the cluster's internal dialogue, showing how the smallest changes in the black hole's accretion rate ripple outward through the entire structure. Phoenix A will remain a benchmark for understanding the limits of feedback, the longevity of starburst activity, and the coupling between energy and matter in the largest bound systems known. Ultimately, to glimpse Phoenix A is to witness a cosmic balance that echoes across scales of space and time. Its extremes, the heat of its plasma, the cold of its filaments, the brightness of its stars, and the darkness of its core coexist in a harmony maintained by gravity and motion. The cluster embodies the universe's tendency toward equilibrium through cycles of imbalance. Each outburst and recovery, each surge of creation and retreat into quiet, contributes to a stability that endures for eons. Phoenix A is not merely a powerful black hole at the center of a distant cluster. It is a portrait of the universe's own nature, vast, dynamic, and self-regulating. In its silent depths, energy and matter continue their eternal exchange, shaping and reshaping one another in a dance that has no beginning and no end, a glimpse into the extremes from which all cosmic order is born.